Hi, good day. I'm Wale, and I would like to teach you a simulation. So it's a very simple one. I actually call it the hello world of simulation. I think if you have been into maybe coding or have learned Python or something, would all be familiar with what a hello world is. So hello world is like the first thing you write now, like the first program. So that's why I think this one is very simple. So first of all, to get this is my Ansys workbench. And I opened the Axis Workbench, and the Axis Workbench is basically what I'll call like an access file that contains different systems. So on the systems here, you have a lot of systems. So you can see harmonic, modal, static, transient, eigenvalue buckling. This is for structure simulation, electric, explicit dynamics. This is for LS Dyna. You can see fluid flow. That's you're going to use Ansys Fluent. You can see harmonics, you can see diffraction, you can even see LS Dana itself again. So you can see magnetostatic. There are a lot of systems. But for today, we are going to be simulating a diving board. So I'm very sure we have watched movies where I say movies, the Olympics or something, where you see a diving board and those divers that jump. And you see how flexible those boards are, right? So we'll try to simulate the design of this on our own system here today. So, and the system we are going to use for it is called a static structural. So if you look towards my left, sorry, you see a static structural here. So I'll click it and I'll bring it out first of all. So under my static structural, you can see a lot of things here, about seven namely. So you can see engineering data, right? So the engineering data is the properties of the material you're using, right? And the geometry. The geometry is the design of the diving board, or generally is the design of whatever you want to simulate. So it's mostly a CAD file. And our model. So the model that I'm trying to look for here, we are using here, is an Ansys mechanical model. So because this is static structure, right? So it's a mathematical model. So I think we should all be a little bit conversant if you have gone further in engineering with what mathematical modeling is. Right? So you try to model a system to make assumptions and get prototypes. So the next thing you see here is a setup, right? You see solutions and you see results. So our geometry, since I have my geometry file with me on my PC, for you to run this, I would give you yours to run the group, is to import my geometry. And I want to use this keyboard that I have because the diving board is basically a keyboard. It's a perfect example of one. And more than a diving board is a keyboard, is also something called a cantilevered beam. So if you have prior knowledge of strength of materials, I think we do it in CV2 too. It's really come in handy, but even if you don't have, it's still really nice. It's something you can pick up again. And I'll make sure I state the formulas, which is very simple here. Now, what you want to do now is to right click this model part again and edit. This edit will carry us to Ansys Mechanical. So I click edit. So you can see here starting mechanical. So yep, so Ansys Mechanical has opened up, and what you can see here, right, is don't get lost in the amount of buttons or keys that is here. They are very simple and intuitive to use. But I think most of the things we'll be dealing with are actually on the left hand side of the screen. Think on this part under outline and detail. So first of all, right, you can always try to get your hands dirty. You can click on as many buttons as you want. But it is for this video. I think let me start with the basics and the simpler ones. So here you can see my model, right? So my model is basically a mathematical model, as I've explained earlier. I can see my geometry import. So my geometry import is the bodies I've imported. So that was the keyboard I put in. Now the next thing you have is your geometry again, and that is our keyboard, and it shows that the body is solid, which is very good. Now the next is materials. So materials, we have defined materials before as structural steel. We defined it under engineering data, right? So structural steel is the default for Ansys Mechanical. If we don't define anything, structural steel is the default. The same way when we are doing CAD, so maybe working with SolidWorks or Fusion 360, the default tool or the default material you find there is structural steel. And if I click it, I'll see the properties of structural steel. You can see derived from Young's modulus and Poisson ratio, Young modulus, and this is about 200,000 MPa, Poisson's ratio 0.3. They are trying to explain to you the value of these parameters. And I think if you're into engineering, this you should already know a lot of these. So the next thing I want to do is my coordinate systems, and coordinate systems, I think I have two, right? So there's a global coordinate system which is here, X, Y, and Z, Cartesian. Lucky for us, I don't think Ansys works with all those other complex ones like polar or cylindrical or spherical. So I think we are working with just Cartesian for now. I don't know maybe if Ansys has any other specific feature I don't know about, but yeah, we're working with Cartesian. And once I click coordinate system, I can see for this body now I have a coordinate system. So I can see that my y is up, right? My x is in this direction, and my z is this other direction, which is good. So I can actually see connections here next. So let me close this connections, but that is going to be blank because I don't have any two bodies that are connecting each other here. I don't have any two bodies interacting with each other. If we have two bodies interacting with each other, then there will be a connection. But as you get advanced, you get used to the concept of connections. So in subsequent videos, I will explain that. But you have this body here. So this is our only body. Now the next thing we have to do is a mesh. Now, a mesh is one of the foundational ideas of finite element analysis. So I think we almost all of us know a Rubik's Cube. And the Rubik's Cube is that thing now that has different colors that we try to arrange. So a mesh is just like a Rubik's Cube. So if I want to analyze the force on a Rubik's Cube, I can analyze the force on each tiny cube on that Rubik's Cube and sum them up together to get the total force on my Rubik's Cube. And that is what finite element analysis is, like the basic idea behind it. So a mesh, right, is just like dividing the body into cubes. So you can hear like complex name for it like discretization, but for solid systems, we use something called finite element analysis. For liquid, we can use finite volume, right? But that one is in later sessions where I'll be dealing with fluids. So for now, right, we have our mesh here. And the quality, so not something when you're simulating, the quality of your mesh matters. It is one of the most important things you can ever do when you're doing a simulation. So I want my mesh to be very fine. So there's a lot of things I can insert, parameters I can insert to change my mesh. Now, what I want to do now is to insert the mesh size. And you can see my geometry, no selection. Under my details here, my geometry, no selection. So what I want to do is to get a body now. So I can click selection, say this whole body, and apply. Now, that is it. Now, so the next thing you want to do now is element size. Now, element size, what you want to do for now is 1.5 millimeter because I want it to be very fine. So next, I'll right click mesh and generate mesh. Depending on your specs, the specs of your PC, it shouldn't take that long, but mine is really done. It's really quick. So I can rotate my body. So you can see it's just like a Rubik's cube stacked side by side. So you can see if I zoom in again, you can see a lot of cubes on it. This one just basically cuts it into cubes. You get. Now the next thing I want to do is I want to define something called the boundary conditions. The boundary conditions is what we use to load the material. So that is what the boundary conditions are. So first of all, since we are working with a cantilevered beam, one end will be fixed, right? And one end will be free. So imagine a diagram now, and let me rotate this. Let me rotate this so you can understand this properly. So this is straight. So here, right, will be fixed to the wall of the pool, or will be fixed to like some staircase where they can jump, right? And here is where the load is going to be applied. Can you see? So there'll be a deflection in this direction. So if you're applying the load here, there'll be a deflection in this direction, which happens to be the negative z. So in this direction, or z, not even negative z, because my axis is upside down, right? So as you can see. So what you want to do next is right click this and insert a fixed support. So you can see it. So let me click the face I want to insert it into. So geometry. So this is icon is for a face. So let me explain something more. You can select an edge. You can select a vertex. I mean that's a corner. You can select an edge. You can select a face. You can select a body. But since we want to click a fixed support, we want to use a face for this. So this is what we are clicking. So apply it here. Apply. Can you see? It works. Now the next thing we want is to define our force. So we insert, right, and we insert a force. Now I want to define this force by my Cartesian axis, right? So I'll click this vector, right, and use components. So I have x, y, and z components, as you can see here. So now my geometry now, I have to click a face that this force will be applied on top. But note that since the diver is going to be standing here, right, on this part, what we want to do is to apply the force on this part. But here is where Ansys differs. If I click a face, the force is going to appear on the centroid of that face. For those who don't know what a centroid is a center of something, and a centroid you'll be taught in ME205. A centroid is like the center. So it can be the center of an area, center of mass, center of pressure, depending on whatever you're analyzing. But since this is a face, right, it's going to be the center of area. So instead of here, I'm just going to put my centroid, my force, right, here at the centroid. It doesn't mean that in my analysis when I'm solving the centroid it is that my load is going to be applied here. No, it is going to be applied here. But since Ansys just directs it to the centroid, we are going to have something here. You can see it, right? So now let me go apply it myself. So my geometry, let me rotate this body so you can have it. So I click again, I want to use a face, apply it to this face, apply. And now, since the diver is going to be standing around here and we have fixed this end, if you notice, the direction is going to be on the z axis as denoted by this blue arrow. You can see, right? So this is z. So let me rotate back again. So this is going to be z. And notice it's positive z, right? So we are going to impute our load, and our load is going to be 500 newtons, right, for now. So this is going to be 500 newtons, which is about almost about the weight of a let's say a little bit of a chubby person. Let's say one on the chubby side, I guess. Now, since we have applied it, if you rotate this body clearly, let me raise this up. You can see, right? I think it's almost at the center. Maybe it's because of the way I'm orienting this page. But notice that Ansys did not put it here. It is towards the center. Now, we have defined our boundary conditions, right? We have a fixed support and we have our force, which is the load. So let's close this for now. Okay, open this. Now, the next thing we want to define is our result. So remember the aim of this analysis is to determine, right, the deflection of the beam, right, when the diver jumps. Can you see? So determine the deflection of the beam. Now, we want to determine something also called the safety factor. The safety factor is whether at this rate that we are loading it as 500 newtons, the body would break or deform. And for a perfect design, a safety factor of 1 is mostly ideal. If it's less than 1, okay, but if it's greater than 1, let's say 1 point something, you are still good to go. Now, what you want to insert now is our total deformation in millimeters. So you right click this, insert deformation, total, not directional, total. Now geometry selection, all bodies, you can see this, right? So if I have a system of multiple bodies, I can scope to a certain body, but since we have just one body, I can say all bodies. Now another thing we want to look at is to verify Newton's law to show our physics is correct, right? So we want to get a reaction force. So let's look at insert. For now, I want to get a probe, and the probe will be my first reaction, my reaction force. So you can see boundary condition, you can see it here. I think I explained what the boundary condition was before. So, and this is a fixed support. You can see it now, right? Now, the next thing you want to do is to insert, and you want to insert a, sorry, give me a minute. Actually, see contact. So, yes, a fatigue tool. So, to get our safety factor, we have to insert a stress tool. So, let's insert stress tool, max equivalent stress. And the next thing we want to do is under our stress tool, we have to get our safety factor. You can see it there. Now, the three things we want are the total deformation in millimeters, right? The stress, the safety factor, and the reaction, just to verify Newton's law. Now, I want to take us back a bit so we can see the math. So, I think we have to go here. So, for those of us who have backgrounds in strength of materials, if we look at this, right, this is a distributed load with pressure on top. Now, the deflection of the beam, right, or that's like the deflection, the amount of length it points downwards, right, is given by this formula for a cantilever beam. You can look through it, but this is the formula, right? And now we have different values. So to determine if our simulation is right, we have to verify our calculations by hand most of the time, right? Since this one is simple, right, we have to use our hands to calculate it. So this is the formula, right, for a cantilevered beam, right, with a load at the end. Now, I is moment of inertia, E is, once again, tensile stress, and let's look at here. We can generate the moment of inertia since we have a cuboid, right? So I is equals to bh cube, the moment of the inertia of the cross section. So our cross section is 17 by 10, right? So that's 17,000 over 12. So this is our value for I, and if you plug in our I value here, you get our deflection to be 1.765 millimeter, right? Now going back to mechanical, anytime you are solving something, the error range should be less than 5%. For it to be acceptable generally as a good result, should be less than 5%. And what we want to do now is to run this to confirm the results. So if it confirms our hard results with less than 5% margin of error, then our simulation is correct. So now I'll right click this and I'll click solve. So depending on the computing power of your PC, it shouldn't take that long. So I think we're back, and lucky for us, my results are ready. So I want to click total deformation, and wow. So if you look at here, right, the maximum deformation is what? 1.75754, and notice our unit is in millimeter, right? And if I come back here, our max deformation is what? 765. So showing that our simulation is correct. First off, at least the physics checks out. I mean, it's one thing to run a simulation, and second, for the physics to check out. So yeah, we are good. So let me play this so you can look at this properly. So you can see it comes down, right? So this is where the deformation is forming when the user jumps, the diver jumps. So the next thing we want to do is, let me pause this, is to check my safety factor. And yep, we are relatively good. Our minimum safety factor here is about 1.15. We are good. So it means that the beam would collapse at about 1.15% of what it is currently loaded at, if I'm getting that right. And yep, you can play a video. Good thing about it is that I actually like when I see the colors actually when they are forming. So yeah, I think the colors flare me up too. So yeah. So what you want to do now is to check the first reaction. And the first reaction here, you can see that as we have it here. Let me put this up. And the first reaction is minus 500 Newton. So voila, we are actually correct. So Newton's law checks out in this system. So our action was 500 Newton, our reaction is minus 500. Can you see? Action and reaction are opposite and equal. And look at now, we are getting a reaction at this end of the beam. Can you see it? This end of the beam, not somewhere in the middle, at exactly this end, at the fixed end. So Newton's law check out. So yep, this has been nice. So let me close this. So I think we are done with Ansys Mechanical. And yep, and you can see all my results are done. And yeah, that will be all for today. Thank you very much.